Well, good evening, everyone. I want to welcome you to tonight's faculty forum on climate change. This is the third in a series of faculty forums that we're holding this fall. They're all focused on topics of extremely high current importance. The first forum in September was on healthcare reform and featured several Iowa State University faculty and members of the community talking about that topic, which is so current and so very important. The second forum in October was on the topic of the economic crisis, and particularly with a focus on recovery. And tonight's topic is one of true global importance. Global climate change. We have several Iowa State University faculty who will speak to that topic, and then will be available to engage the audience in discussion. The panel tonight will be moderated by Professor Gene Tackley. Professor Tackley holds his faculty appointments in agronomy and in geologic and atmospheric sciences. He's a leading researcher on the impact of global climate change. He served as a consultant on climate change for NASA, for the National Research Council, for the National Science Foundation, and the United Nations. And he was a member of the Intergovernmental Panel on Climate Change that was a co-recipient of the 2007 Nobel Peace Prize. Professor Tackley will make a few opening comments and then introduce the speakers for their presentations, followed by the question and answer session. Professor Tackley.
Thank you, President Joffrey, and thanks to Pat Miller for organizing this event. And tonight we'll have four of us will be making short presentations to kind of get some issues on the table, and we hope this will really help to stimulate some good questions and some good conversation as we go along. And the people who will be speaking tonight, Bill Gutowski, my colleague in Geological and Atmospheric Sciences, holds a bachelor's degree from Yale and PhD from MIT, came to Iowa State in 1991, and then following him will be Ray Ehret, who also is in the Department of Agronomy and has his bachelor's degree from the University of Virginia and PhD from Colorado State University, came to Iowa State in 1993. And John Miranowski, professor in the Department of Economics, is a graduate, has a bachelor's from Iowa State and a PhD from Harvard, came to Iowa State first in 1975 and then was at the Economic Research Service of the USDA for a period of time and then came back to Iowa State in 1995. So we have, and all have research, active research in this area of climate change. So we'll get on with it. I'll start with just a few brief comments on the dilemma we face to just kind of set the stage a little bit and try to emphasize the urgency of the issue we face. Bill will come with a look at extreme events. He's an expert in this and has co-authored a major U.S. publication on this topic. Ray Ehret is one of our leaders in regional climate modeling and is leading currently a major international effort in regional modeling, as is Bill. And then I'll talk a little bit about the impact of climate change, and John will sweep it up with the economics. It all comes down to economics, I guess. So that hopefully will really get us started, get us thinking, and get us off to some discussion. So let me just start with a little bit of some recent update. In March of this year, there was a meeting of scientists in Copenhagen to bring together the most recent science since the last Intergovernmental Panel on Climate Change in 2007, which Bill and Ray were both parts of, too, in authoring that report. But in Copenhagen in March, one of the results that was shown was this result of global carbon emissions, and the projections that were started back in the mid-90s that were the basis for the discussions in Kyoto had projected carbon emissions out through the 21st century. The current results are that emissions are higher than the worst scenario envisioned in the mid-1990s. And so that means that the projections for climate change that have been laid out in the third and fourth assessment reports of the Intergovernmental Panel, which have the increase in global mean temperature anywhere from 1.5 to 6.5 degrees, perhaps we are too conservative, that the actual range may be up with the highest that have been, or higher than those that have been projected. And so one of the issues that was discussed in Copenhagen was how can we set some meaningful target that the world needs to shoot for in order not to create dangerous anthropogenic interference with the climate system. And it was agreed that the 2 degrees above the pre-industrial level would be one where that could be tolerated with at least a 50% chance that we would not interfere with have dangerous interference with the climate system. And so that's the issue that we'll be talking about a little bit later. And if we translate that into emissions, that means that rather than follow this trend that we're on right now, we have to be following a trend like this. That means that our emissions have to peak by 2020 and go down from there down to toward the end of the century be below zero, that is, negative emissions. This is a daunting task. And so this is the issue that's in front of us. So we'll turn to Bill to talk about climate extremes.
Okay, thank you, Gene. The reason why we want to talk about extremes is that when we think about how weather and climate affects us, it comes through usually when we talk about extremes. Extreme weather, hurricanes, strong thunderstorms, and other extreme climatic events like extended droughts. So changes in extremes then become very important when we're talking about climate change because it's a major way that climate change ends up impacting human society and also natural ecosystems. Now Gene very nicely introduced the issues of greenhouse gases and their changes, and also he talked about the warming effects that we can expect from them, rises in temperature. I want to take a little bit of a step backward and talk a little bit about the greenhouse effect itself because that really helps set the stage for understanding how extreme events may be changing in the future. Our planet is warmed by the sun, as I think we all understand, and we get a lot of heat energy from the sun. A lot of it ends up going back into space. It's reflected back into space, but the Earth absorbs a lot of it as well. And then the Earth radiates, because it's a warm body, it radiates some of that energy back to space. Now, because the Earth has an atmosphere, some of that energy that's being sent back to space gets intercepted by the atmosphere and comes right back at us, as suggested by these arrows here, and that's the greenhouse effect. It ends up keeping our planet warmer than it would be if we didn't have an atmosphere. Now, when we increase greenhouse gases, we increase the heating of our planet. And so we end up having more energy coming back, and that, of course, leads to many things. Among other things, it warms our planet, but it also has other implications that are important to think about. It leads to more energy for storms. All that heating ends up producing more energy that can drive more powerful storms. Also, because the atmosphere is warmer, you can have more water in the atmosphere, more atmospheric moisture, which means more can fall out as rain. So there's more water in the atmosphere, more energy for storms. And that means there's a great possibility that you can have more extreme weather, or the extreme weather that does occur can be even stronger than it would have been in the past. One of the most dramatic ways that this has been seen is when we think about Atlantic hurricanes. Certainly hurricanes have very damaging effects already. The concern is how they might change in the future. This diagram here was something that was produced by Kerry Emanuel, who actually spoke here about a year and a half ago, I believe, talking about climate change issues. There are two curves. The curve here, the blue curve is ocean temperatures in the tropical Atlantic that from 1950 up to 2010, or almost 2010, going forward in time. Then this other curve here is a measure of the power of hurricanes that Cary has devised. And there is a very strong relationship between the power of hurricanes and ocean temperatures, and it raises very important questions. What's going to happen when ocean temperatures warm up in the future? Well, if we look towards the mid-21st century, and this is using just one of those more moderate scenarios that Gene was talking about, not the more extreme ones, those scenarios suggest that we'll have temperatures that are 0.5 degree to 2 degrees warmer as it is, and taking advantage of the kind of curve that Cary has here, that suggests that hurricanes could be 35 to 70% stronger. So when hurricanes do form, we could end up not only having hurricanes, but having hurricanes that are more powerful. And that's also suggested by various types of more theoretical studies that people have done over the years. This light curve here is a depiction of the frequency of hurricanes in present climate, and then this here represents hurricanes moving forward in time. And the tendency is that storms that might have been Category 4 storms are going to more often be Category 5 storms. Category 3 storms become Category 4 storms. Stronger hurricanes. Now, hurricanes don't mean all that much to us here in central Iowa, thankfully, but we do have to be concerned about other types of changes in extreme weather. One of the things that we've been studying is how weather in the middle of the United States may change and produce heavier precipitation. One way that we've been looking at this is circulation patterns. This is an example from some of our studies that shows how the winds blow when you have particularly heavy rainfall events here in the middle of the United States, rainfall events that affect us. This pattern is kind of like with what we had in our weather just a week or two ago when we had those heavy rainfall events that occurred that dropped 3 or 4 inches of rain on different parts of our state. What we have found is that the circulation patterns will probably remain about the same in terms of patterns that produce extreme rain in the present and future climate. But what's going to be different is the atmosphere will be warmer. And I'll go back to that point I mentioned earlier, that a warmer atmosphere can have more moisture in it. And so again, that means that if we think about the moisture flow that's coming northward because of this circulation and look at future climate, again, looking at what's really a more moderate scenario of greenhouse gas increases, we see that temperatures toward the middle of the century are going to increase by about 2.5 degrees or so, and that leads to a situation where some of these extreme precipitation amounts on the order of 4 to 5 inches per day start to become 5 to 6 inches per day. And those 3-inch rainfalls that many parts of our state had about a week or so ago would end up being more like over 3.5 inches of rain. That added rainfall is not simply just some nice additional percentage amount, but you're already adding it on to an amount that's close to creating floods. So all that extra water has to go somewhere, and it means you're more likely to have flooding as well. So, just to wrap up this section, global warming means more energy for storms, more moisture for storms. Hurricanes, when they occur, are likely to be stronger. We can't say anything yet about whether or not hurricanes will occur more or less frequently, but when they do occur, they're likely to be stronger. Locally, we're more likely to have more intense precipitation from our heavy rainfall events. And I haven't even gotten into another important consequence of climate change, which are droughts. And even though we may have heavier rainfall and more flooding, what may seem contradictory is there's a great chance that we may also have longer periods of dry weather, which could mean more severe droughts as well. We can talk about that later. But right now, I want to pass the baton to my colleague, Ray Ehret.
Thanks, Bill. We hear a lot about global climate change and the change in global temperatures, but I'm going to talk a little bit about regional climate change here. If you think about it a little bit, there's really a mismatch of scales. We talk about the average global temperature going up by 2.5, 3, 4 degrees or whatever. But what does that mean to us? If you're a farmer trying to figure out what kind of crops to plant, if you are an electric utility planner trying to figure out where to build a dam so that it will have water that will fill it up and what your electric load is going to be in the future, the average temperature of the Earth is not a particularly interesting or useful number. What you care about is the change in climate in the place where you live or in the territory where your company operates. So while we look at global climate change as global, because we have to, because all of the Earth is interconnected, when we look at effects, what impact it's going to have, those tend to be local. Those tend to be regional. They occur in watersheds, landscapes, countries, smaller areas in the whole globe. So the problem that we have then is how can we get information at these decision-relevant scales where we feel the impacts of climate change from coarse global projections. And that's one of the things that we've been working on at Iowa State for about the past 10 years or so. Look at this nice landscape. This happens to be in France, a region. All of the landscape you see here, from the hills to the valleys, back up to the mountains in the distance, is less than one grid cell in a global climate model. What we do in a global climate model is to solve physical equations that govern the temperature, the movement of air, all these other things at points. But because we're looking at the whole world and we're trying to do this for 100 years, those points can only be so far apart. We can only solve them at a fairly coarse distance. And to give you an idea of that, here is one of the models that was used in the third and fourth assessment reports of the IPCC. It's run by the Hadley Center in the United Kingdom. My mother-in-law lives in a condo on Miami Beach. She's not in a houseboat, okay? So you can see that the models that we have these days are fairly coarse. They have the continents, they have most of the other features of the Earth on a very broad scale, but we can't focus down very easily at all to places like Iowa, to places like certainly Florida that doesn't even exist, to much of California, and so forth. So we need some way to get regional detail out of these very broad-scale results. If we could take this grid, which is on the order of 200 to 300 kilometers or so in terms of the spacing of the points, and somehow solve the same equations at points that are, say, 50 kilometers, 30 miles apart, we would get something that looks much more like the U.S. that we know, much more like North America. The problem is that we don't have the computer power and other resources to do this all over the world. So one of the approaches we've been taking is to do what's called downscaling. We take these coarse-scale global model outputs, feed them into a finer scale model over a limited area, and then try to extrapolate the climate in a particular region from that. These models are based on the same physical laws as the global climate models. These are things like Newton's laws, the first law of thermodynamics, and so forth, and we expect that those laws will hold in the future. So we have some confidence in our projections from these models. The problem is that this approach is very intensive in computer and human resources. It takes months and months to run one of these simulations, and it produces many hundreds of gigabytes or terabytes of computer output that you have to somehow distill down into a form that will be meaningful to people. So there's a second approach, which is called statistical downscaling. The way that works is that you derive statistical relationships between the results of your model and the observations of climate. So essentially you use your model to simulate the current climate and then derive statistical relationships to observations. The problem is that we don't have observations of the future. Okay? So we don't know if the same statistical relationships we find for the current climate are going to hold in that future climate. So we've got two different methods, each of which has their advantages and disadvantages. The one we've focused on mainly at Iowa State is dynamical downscaling, and there have been quite a number of collaborative dynamical downscaling projects, several of which have been led or at least have had participants from those of us at Iowa State. One of the earliest projects, and possibly the earliest project of this type, was one that we started around 1996, just when this technique was starting to develop. And that had 12 different members. We've been recently involved in the North American Regional Climate Change Assessment Program, which is currently ongoing. One that we've been leading over the past year or so is looking at global seasonal forecasts rather than climate change forecasts. This is a particularly interesting problem because it's of immediate practical relevance. If we project the climate for 2050, well, many of us in this room won't be around in 2050, okay? What we're doing now is we're trying to see if these same methods can be used for seasonal projections of, say, 3, 4, 5, and 6 months. We do hope to be around then, certainly. So if we could get, say, a projection of next spring's planting season starting from now in November, that would be something that would be very valuable to people. We're currently engaged in that project with sponsorship from the National Oceanic and Atmospheric Administration, and we have 11 agency and university partners that we're working with on this. And we hope to have some results from this within the next 6 months to a year that will tell us whether it's practical to apply these same methods we've used for climate to shorter scale predictions on the seasonal scale. I'll pass the baton back to Gene now, who will talk to us a little bit about some of the impacts of climate change.
Of course, Ray was too modest to say that he's the one that's leading that major project that he just talked about. What I wanted to mention here is coming back to impacts and to if the temperature should rise at this to this 2 degree level or above this 2 degree level, what would be impacted? And so this is a kind of a complicated slide, and you may not be able to read all these on the back, but the left-hand side was developed for the third assessment report in 2001, and the right-hand side was for the fourth assessment report in 2007. And each of these gives a risk which increases with increasing global mean temperature. And so we now have come about 0.6 of a degree above the pre-industrial level, and this 2 degree guardrail was set here as 2 degrees above the pre-industrial level. So we have 1.4 degrees of margin before we get to this level. And in 2001, this was for instance, here on the left-hand side, the risk to unique and threatened systems. If you raise it, you get into the red zone, which is a much higher risk. Well, you see, if you compare the more recent results with the early results, that even the 2 degree guardrail is going to have a strong impact on some of these threatened systems. Risk of extreme weather events, which Bill already talked about. You see in 2001, we thought we were in the yellow area. Now that's very likely to be in the red area, even with the 2 degree warming. And so the urgency has come up substantially even since the 2001 report. So sometimes we ask, well, what are the impacts? What could possibly happen? As Ray mentioned, these impacts are local. They affect us locally. So some of the things that we're doing here at Iowa State with some colleagues are to look at stream flow. And Bill mentioned the increase in precipitation events. And we found both from studying stream flow with our colleagues from CARD and Department of Economics, and also from Ag and Biosystems Engineering, where we looked at tile drainage flow, that when you get enhanced precipitation, it magnifies both stream flow and tile drainage flow. So a 20% increase in precipitation, which we simulated for the middle of the current century, 20% increase in stream flow translates into a 20% increase in precipitation translates into a 50% increase in stream flow. And a 30% increase in precipitation translated into an 80% increase in tile drainage. So those are the kinds of impacts that even a small change, relatively small change in precipitation can create. Soil carbon dynamics with our colleagues at St. Louis University find that higher temperature and precipitation accelerates the loss of soil carbon because it speeds up microbial action. And so it's working against our efforts to sequester carbon. Pavement performance. Working with colleagues in civil engineering, it turns out that cracking and rutting of pavements, both asphalt and concrete, increases with increased temperature and precipitation. So we're working with both colleagues here and also colleagues at the National Center for Asphalt Technology on how to model future pavement performance in order to create the right mixes for concrete. Crop growth, more precipitation, and lower temperatures that we have seen in the central U.S. have actually increased yields. So we've seen an increase in agricultural yields with earlier plantings and more favorable precipitation and considerably more favorable temperatures. We don't get 100-degree days in Iowa anymore. Had 6 in the last 20 years. We've had years when we've had 13 days above 100 in a single year, but we don't get those anymore. So that's more favorable for agriculture, and we ought to be taking advantage of it. Wind speeds, we published a paper a couple of months ago that wind speeds across the U.S. are declining. Surface wind speeds are declining, have over the last 30 years. That decrease is not favorable for crops. Crops need ventilation. They need drying effect of winds to reduce dew and fungus growth and so on, and also air pollution from our cities. In our cities, we don't know the impact on wind power. We didn't study wind speeds at 80 meters, where turbines have their hubs. Also, Fred Jansen in EEOB is studying the temperature-dependent sex determination for turtles, a probability that males hatching from eggs declines with temperature. So you get a preference for females as the temperature goes up. So it has an impact on the ecology of turtles. Just some examples of some of the interesting research relating to climate change that maybe you don't think about when you think about impacts of climate change. Well, when we think about impacts to societies around the globe, we have to realize that climate change is a risk multiplier. If your society is at risk for some reason, whether it's food shortage, access to good health care, access to fresh water, if it's already prone to sea level, to inundation and sea level coastal areas, climate change is a risk multiplier. It's also true that impact is most severe for those least able to cope. And so it becomes not only a problem for major governments in terms of their major infrastructure, but it's how they deal with the people who are least able to cope. Many parts of the world are already feeling negative effects far worse than we are in the U.S. People who depend on glaciers for their water supply, and they're finding that these glaciers are melting. And they're not, in 20 years, they won't have access to that water during the dry season, as happens in the downstream of the rivers in the Andes. Basic needs, food, water, energy, are becoming increasingly at risk in many of these countries. And because of that, climate change is now viewed as a global security issue. That is, if we have very large societies at risk, what does that mean for social unrest? We here at Iowa State, because we have such a wide range of capabilities in the fundamentals of food, water, and energy, we have a lot to offer in terms of application of solutions and adaptation skills at dealing with climate change. So I'll turn it over to John for the economic side.
Thanks, Gene. As Gene said in starting out tonight, I'm kind of the cleanup hitter, or the closer is another baseball analogy right now. One of the things that makes it very challenging in terms of the economics of climate change is that there's so much unknown about the future and the direction things are going to take. And at the same time, we're sitting here trying to value some of the impacts and trying to figure out ways of intervening to change the course of climate change. If we do not intervene, it could be very costly. And I think this is basically the basis we're starting from, and it could result in catastrophic changes. But the big economic challenge here is deciding how much to intervene and when to intervene, and in addition to that, even how to intervene. Because there are a couple ways we can do the intervention and still come out with a fairly reasonable solution. One is we can do research, development, and new technology and adapt to some levels of climate change. And that gives us a real opportunity to, without incurring necessarily great costs, figure out, in a sense, how we can live with the climate change. And the costs, another factor is that the costs are going to sometimes be lower if we delay mitigation to the future when we've got better technology and we're a richer society. Now, some pundits are taking this to the extremes and saying, okay, well, let's just wait 100 years and then we'll do something because we'll have all this fancy technology. I'm not arguing that at all. But sometimes the timing of those changes can be very critical in finding the most cost-effective way of dealing with climate change. I don't want you to get hung up in the equation that runs across the top of the page. That's not the purpose of this, but I wanted to illustrate a couple points that are very important when you're doing an economic analysis of climate change. And typically what we do is that we do it from what's called a net present value basis, and that is simply the present value of the costs plus the benefits. But the thing that really complicates this whole process is that the benefits and the costs occur year after year after year into the future. And in the case of climate change, we're looking out 200 years, 150, 200 years, very easily in this process. And so these costs and benefits are going to be occurring all along the way. Now, typically in economics, we discount, and that's what that little 1 plus R is here. R is the social discount rate. Why would you discount? Well, the reason our argument or rationale for it is we prefer $1 today to $1 sometime in the future. And if you don't buy that, if I offered you $1 today or $1 a year from now, what would you take? Is there anybody that would want to wait a year? No. I mean, you can invest that money for a year. I mean, savings rates aren't very good right now, but you can invest that money for a year, or you'd have it today, and in a year you're going to be waiting. So what we're doing essentially is taking this out into the future and discounting it. Now, why does this matter? Well, in the benefits and costs over time, they're based on the assumption that we're making assumptions about what economic growth is going to be. We're making assumptions about what technology is going to be. We're making assumptions about what population levels are looking like. I mean, we've got projections, but we're making a lot of assumptions along the way, and also we're making assumptions about energy use in the future. And we don't know these with any degree of certainty at the present time. Also, the timing of benefits and costs matters when you're discounting more, because these distant benefits and costs out here don't count nearly as much as the benefits and costs today and in the next period. So what we're trying to do is put these on a comparable basis and add up to one value here that measures the value of our intervention versus the cost of that intervention. The smaller the R, the more weight we're putting on the future. There's a famous report came out of England headed up by an individual by the name of Stern, and they used a 1.4% discount rate. What does a 1.4% discount rate do? Well, $1 of harm avoided in 2200 is going to be worth only 6 cents today when you discount that dollar back to the present. But if we use another discount rate, let's say 4%, doesn't sound a lot higher, in $1 of damages avoided in 2200 is going to be worth about 0.03 of a cent. You got it flipped over here to the bottom line today. And so anytime you start using slightly higher discount rates, even your savings account is probably going to yield you more than the 1.4% today in the process. And so what we're saying is if you have much above that, these things aren't going to be worth much out here when we bring them back to today. And that's why this is a very important piece of the puzzle in terms of discounting. Okay, in choices between mitigation reducing the temperatures and adaptation, living with a certain amount of temperature increase, the costs of global warming increase as the temperature increases. The costs of mitigating global warming fall with temperature increases. Some estimates I've seen would say that if you had tried to reach 450 parts per million in the atmosphere, you're probably going to spend several $1 trillion to achieve that kind of a goal. It'd be very costly to society to get there. At about 550 parts per million, we're looking at a few $1 trillion. If we want to let it go up to 650 parts per million, we're probably dealing with less than $1 trillion. So these have very big costs associated with trying to get down to these lower levels through mitigation and not trying to adapt at something like 550 parts per million. There's a trade-off between mitigation and adaptation. Let me talk about a little bit about the Stern report. Basically, they estimate to avoid a 1 meter sea level rise is going to cost about $1 trillion using that 1.4% discount rate. Seawalls around the U.S. to protect against a $1 meter sea level rise is going to cost the U.S. about $7.5 billion. So adaptation is a way in dealing with this to a point. But if it gets too far out, then we might face catastrophic things that we can't affect. And so these are some of the trade-offs. But as Ray was saying, these impacts are going to differ by region, by location, by country size, and by level of development. And so this becomes very complicated when we're looking at it. And it's also a temptation for people to free ride. Because if somebody else does it, then maybe in my part of the country, I'm not going to pay dearly in the process. This is an indication of the global damages as a percent of GDP for 3 different scenarios. There were 5 originally, but the lines got a little cluttered, so I just want to deal with 3 of them. The top line here is the business as usual. And if you look out to 2150, we're looking at about a 1% of global damages of GDP is going to be lost in the process due to those global damages. If we put together an adaptation, if we use adaptation, R&D, and mitigation, we're going to be able to drop that down to something like about 0.5% of GDP. If we use the mitigation only, we can only lower it to about 0.8% of GDP. So you've got, you can go business as usual with about a 1% loss. You can go with mitigation only with about a 0.8% loss, or you can use a combination and get it down to about 0.5% loss. Let me move on to talking a little bit about policy. These 2 curves, the marginal benefit curve is just those discounted benefits from before, with different levels of greenhouse gas reduction. And the marginal costs is just the costs from before with different levels of greenhouse gas reduction. The costs rise as reduction rises, as we said before. The benefits decline, and we can mitigate to some extent down on this level. Okay, when we come along with policy options, what are we hearing about now? Everything is cap and trade. And when you talk about cap and trade, what we're saying is we're going to cap the amount of greenhouse gas reduction or cap the amount of carbon that's being emitted. And if we cap that at this particular level on the graph, then what we're saying is that picking that point because that's where the added benefits and the added costs of intervention or reduction are equal. So society is going to be best off with that level of reduction. That would, in turn, give us a price over here of a permit if we were trading permits. Now, we can accomplish the same thing with a tax policy. And a tax policy would give us the same thing, only it would say, okay, we're going to set a price here, or a tax here, and that would give us the same reduction in the process. Now, there are other ways of doing this also. We hear a lot about regulatory approaches. We hear a lot about subsidizing biofuels. But what do? They don't give us the least cost of getting there. They give us a cost curve that many times might lie to this side of achieving that reduction. So if we're going to focus on some of the other regulatory policies, what they're going to do is cost us more and get us further, or not get us as far in terms of reducing carbon in the process. The market-based solutions basically, I think, are the easiest way to go in making the system work. And let me give you a couple examples. If we tax just the carbon from the primary carbon emission sources in the country, we're looking at about 1,700 firms. They're the producers of gasoline, and diesel, they're the producers of natural gas, the producers of coal in the process, and power plants that are using. What we can do with that is we can control about 85% of the carbon that we've got available out there in the process. Very little administrative cost, simply a tax at that point in the process. And what does it do? Well, it reverberates throughout the whole economy. Why? Well, if you're a farmer, what's going to happen? You're going to pay more for the fuel you use. You're going to pay more for the fertilizer you use. You're going to pay more for the gas to dry your corn in the fall. And how are you going to behave? Well, if this is going to cost you more, you're going to find out ways of using less of it. And so you're going to adjust your operation. If you're a consumer, the price of gasoline goes up because of the carbon tax. What are you going to do? You're probably going to drive less. You're going to buy a more efficient car. If the cost of heating your home goes up, you're probably going to insulate more. You're probably going to put in a more efficient furnace. All of these things would reverberate throughout the economy with very little administrative charge in the process. We could use a carbon cap with carbon permit trading. That is another way. Again, I would focus on those same primary emitters. We have something like that right now on the Chicago and on the London Climate Exchange. You can go in and buy carbon contracts. And a lot of those carbon contracts, in the U.S. at least, are coming from farmers who are using no-till. There are consolidators like Farm Bureau and Farmers Union that are consolidating these as a way of providing an offset to the carbon in the process. The London Climate Exchanges work more efficiently. Why? Because Europeans under Kyoto are trying to reduce their carbon. That makes carbon more costly, so the price goes up on the markets. We have a market for this right now in Chicago for sulfur dioxide. It was something that EPA and the Clean Air Act implemented several years back in about 95. Works very efficiently. Prices, I think, are someplace in the range of $50 a ton of sulfur dioxide. We can subsidize alternative fuels. But I'll come back to that one in a few minutes. And we can have research and development incentives to try to develop new alternatives and new fuels. The one thing I worry about is the government picking the winners. We decide which projects we're going to fund. It may not be the best technology, but we decide this is the one we're going to fund right now. If there were a better set of incentives simply for taking those risks and so forth in developing these technologies, that would be something that would add greatly to the process. Now, we could also go the route of regulatory alternatives. We've got a low-carbon fuel standard in California under the California Air Resources Board. And what they're saying is you can only use fuels with a certain level of carbon reduction in them. We could mandate the level of biofuel blending, as we have under the Renewable Fuels Standard 2, with a low-carbon fuel standard saying that you can only produce it with a corn ethanol with a 20% reduction, cellulosic ethanol with a 60% reduction in carbon over gasoline in the process. But that isn't particularly efficient. And Let me just give you a couple examples from research at Iowa State. Gene has alluded to some of these already. I just want to talk about a couple that I've been involved with. One of these is we looked at what kind of a carbon credit would you have to give to cellulosic ethanol market to have a market. In other words, what would processors pay for cellulosic ethanol, and for cellulose feedstock, and what could they pay for it, and what would farmers be willing to accept? And if those two are equal, we have a market. And if they're not, we have to find some way of getting that price up there in the process. Now, the way we've chosen to do it so far is to do it with $1 tax on cellulosic biofuel, or not tax, but subsidy for cellulosic biofuels or tax credit. And in addition to that, there's a collection, harvest, storage, and transport subsidy up to $45 a ton. Okay. This is what it would cost in terms of a carbon credit for corn stover to get it to go into the market today. This is what it would cost for switchgrass in Appalachia. This is what it would cost for wheat straw in the Pacific Northwest. The one thing I want you to look at here, we're looking at tax credits or subsidies of over $100 a ton to get most of these into the solution. Now, how are we, this is if we took away all those credits. Now, turn this around and you've got another interpretation. What if we mandated that we had to have 16 billion gallons of cellulosic biofuels blended by 2022? And we haven't. So this is a rough estimate of what it would cost us today for each of those tons in terms of subsidy or what the consumer is going to pay for very expensively mandated cellulosic biofuels. I've served on a panel the last couple of years on alternative liquid transportation fuels of the national academies. And we did this for all kinds of fuels, coals to liquid. We had carbon sequestration, capture and storage in the process. And what we came up with is even with a $50 a ton tax, nothing could compete with oil unless you had $100 a barrel oil. At $60 a barrel, nothing competed. So to get these biofuels into the solution is going to be very costly. The last thing here is I just wanted to mention is U.S. average yield. This is just trend lines for corn. The point I wanted to leave you with here is, as Dr. Tuckley was mentioning, the corn yields are probably going to be increasing. This is the trend up through 2008, the trend that's existed since 1960. The yellow line here is the trend since, with a break in about 97, where we've got a faster growing yield trend. And up here is one if we had a 300 bushel an acre corn yield target by 2030. Now, the reason I'm saying this is corn companies are talking about this kind of technology increase. That may be way too high. But if we add to it with a little good climate change, in a sense here, we may come close to that. Why is that important? It's very important because we talk a lot about indirect land use change and the fact that we're not really saving it with biofuels. But if we had more rapid corn yield growth, biomass yield growth, and so forth, what we could be doing in the process is freeing up land so we wouldn't be going on to new lands in the process. And the carbon footprint or burden of these crops and the biofuels would be reduced substantially, and things could work out a whole lot better in the process. With that, I'll turn it to questions.
Okay, so now it's your turn. We'll bring our panelists back up, and we'll like to entertain questions that you might have on presentations or other issues that come to mind on this topic. We have a microphone, and I guess it'll be, so if you could come to the center mic And you can just line up there if there are more than want to. Who's going to break the ice on this? Well, I'll break it. John, climate change only goes so far in increasing corn yields. I mean, we can get more precipitation, we can get more favorable temperature, but we're not going to get more solar radiation. And photosynthesis is the fundamental that's needed. And if you lay on your back in a cornfield, it's pretty dark down in the bottom. It's pretty much all used up. And furthermore, it takes a lot of water to raise corn. And when I was growing up in Minnesota, we planted 14,000 plants per acre. Now they're planting 32,000 plants per acre. You can't go much higher in density. I argue with this issue of being able to use the traditional method of planting more plants per acre and trying to capture more sunlight from someplace. So you want to respond to that one?
The only thing I would say is I'm just using that number because that's one that's been thrown out by the seed companies. I think the important thing here is that if we can get even a slightly more rapid rate of yield or increase, that's going to help substantially in terms of our ability to adjust.
Yeah.
And I'm not saying it's going to go up that much. I think there are things that could lead to greater productivity in terms of management and so forth. How much extra water we're going to need is an unknown. And there are a lot of areas of the country where, particularly in the Ogallala, south of Nebraska and so forth, we're not going to get any more water. That we're going to lose land in the scheme of things. So it's, all we're saying is that if it was slightly higher, it may make a difference. And what we're trying to do is look at the trade-offs on land use in a bigger land use model process.
Good. Question?
Yeah, my question is for Dr. Markowski. I have two questions, actually. One is, has there anything been studied on the willingness to pay of people who are confronted with the choice to mitigate or adapt? What's the willingness to pay for people who have that choice? Number one. And my second question is, how are other variables like the environment and other things, take your choice of any other variables, other than just on human impact considered in the cost-benefit analysis of global climate change?
Okay, I am not an expert in the area. I do know that other climate impacts are taken into account other than direct human impacts. For instance, one of the things we were talking about, yields up here, if we have climate change, it's going to affect the way I have to grow corn here. Because if we don't get the hard winter freezes, we're going to have a whole series of new problems up here. All we have to do is look at soybean rust and see it staying down south, and then it migrates up here in the summertime sometimes. So those kinds of things are all taken into account on what kinds of adjustments you might expect. Even some of the ecosystem destruction or disturbances are being considered in this process. What people are willing to pay, I think what they're willing to pay is to find the cheapest way of dealing with climate change. One way of dealing with it is mitigation. Another way is adaptation. That Stern report used something like a $14 trillion health cost if we don't do anything, if we do business as usual. But think of all the things that could be done to avoid that $14 trillion cost. It might be spraying for mosquitoes for malaria and other types of diseases in the process. All of those probably would be much less than $14 trillion. I think the World Health Organization has about a $100 million budget. So those are big numbers in relative comparison. Thank you.
Other questions?
This this is a question for whichever of you would wish to answer. I don't quite understand adaptation as being an alternative with mitigation when there's so many uncertainties with both, but certainly why do we think adaptation is possible? What is the risk that no adaptation that we do at the present time would ever be enough, for instance, and also the risk with mitigation? It seems to me that I've read a lot about positive feedback cycles, that if we set them off, whatever we do, it's not going to matter a whole lot. So I would kind of like to know how close are we to those? How realistic, or what probabilities are connected with those? And one final thing, I mean, the idea of corn, from what I've read, it's not very well balanced for the human diet as far as omega-3s and 6s, the ratio, and we don't understand yet what it really means to human health to have a different ratio than the ratio our food had before. And so 10, 20 years from now, the wealthy people that can choose their food might not even want a corn-based diet. So even that assumption of, growing a lot of corn isn't necessarily there, I don't think. So anyway, let me sit down and you have at it.
Okay, you covered a lot of issues there. Anybody want to jump in on the adaptation versus mitigation one first?
Basically, what it all comes down to is the management of risk. Okay, one of the ways that I've heard.
I'm hard of hearing.
Okay, it all comes down to the management of risk, and you can look at the adaptation versus mitigation dilemma as sort of saying that adaptation is managing the unavoidable, and mitigation is avoiding the unmanageable. That's one of the ways of looking at it. So what we need to do is to try to get our best assessment of what the risks are of some of those things you've mentioned, of the sudden and catastrophic climate changes, what some people call climate surprises. And then those of us on the physical science side can inform people like John, who can then help society in establishing what the costs will be to avoid those sorts of things, as opposed to the costs of adapting to them when they should happen. So it's very much a problem that requires the merging of both the physical science side and the economic and social science side.
Anything else on
the only thing I would say is that probably the best way to look at adaptation is the fact that the climate is always changing. It may be getting colder, it may be getting warmer, it may be getting more variable or less variable. And we have historically continued to adapt. There was a time when air conditioning was a rarity. Now we have air conditioning as a way of dealing with things. We heated our homes, we never cooled them, except by natural cooling. And that's a form of adaptation. And I think a lot of times we do things without ever thinking of them being adaptation. And I think that's where I see us adapting to some amount of change. But as Ray was saying, where I have my concern and the dismal science of economics has its concern is with those catastrophic events. And that is at a pretty high level of climate change where the risk of that happens. And those high-risk situations are ones that we have to avoid at all costs.
One other thing about adaptation is that we've always had climate change, as John's pointed out. One of the issues we're dealing with now is that the current changes are very rapid, and that they aren't ones that will turn around in a short period of time. So we're looking at And you have to remember that society as we know it now has developed over the last 200 years, and that's pretty short on the scale of human existence. So we know there have been societies that have existed for 200-300 years successfully, and then comes a period of drought. They tried irrigation, and it didn't work, and so they died out. In fact, there's never been a civilization that has survived that has tried to use irrigation to produce food, and that's a sobering thought in my mind. To what we have today globally as our society. And there are some societies like Saudi Arabia that's given up. They tried it with irrigation, they tried raising wheat, and they just gave up. It cost them 5 times the world price to raise wheat, so they just quit. And they're never going to raise wheat again in Saudi Arabia unless wheat gets to, $30, $40 a bushel or whatever. So we now have changes that are very rapid, and they aren't ones that we can bridge across in many cases with some kind of transition technology. We have to take sea level rise. You mentioned what would it take to adapt to 1 meter sea level rise. Well, that's a foregone conclusion within this current century now, according to the latest data. I didn't show that. That was also discussed in Copenhagen. We will very, very likely see 1 meter rise in sea level, which puts most of the Everglades underwater, puts Key West, St. Petersburg, Tampa, and Kennedy Space Center underwater. So we've already got a cost that we better start thinking about. And that's not if we walk home and shut the lights off. I mean, we're already committed to that one.
What's the potential for carbon sequestration in tropical farms? And is it economically feasible for countries in the north to subsidize tropical farmers using techniques to sequester carbon?
You can think about sequestration in terms of above-ground biomass, in terms of wood, for instance, woody materials, or you can think of it as below ground. Tropical soils typically are not very good at storing carbon because it's, at least in the moist tropics, because it's moist and it's warm, and that encourages decay. And so tropical soils are not very rich in carbon and can't hold a lot. At least that's my thinking. There are others that maybe are better able to talk about that. But so it's mostly above ground, and so certainly restoring tropical rainforests is a kind of a no-brainer. I think that would certainly be a good thing. I don't know. I don't have numbers on the magnitude of what amount that is. But when you start thinking about the amount of carbon that each of us puts into the atmosphere and what it would take for each of us to clean up after ourselves, it's a daunting total. I probably put in 30 to 40 tons per year. So when I think about how many trees I'd have to plant in my backyard to take up 30 or 40 tons this year, much less clean up after myself for the last 20 years, it's an enormous amount.
Okay, so I was wondering, it seems to me like a lot of this climate change kind of correlates with human population. And do you think that maybe focusing a little bit more on capping human population growth would putting a lot less pressure on all the demand for energy and the demand for food and the demand that is driving all this technology and this pollution and whatever else that's causing this would be would be a good way to kind of cap a lot of this? And also, isn't there some kind of lag time before we see the results? Because it seems like right now there's a lot of focus on trying to subsidize all these new technologies and stuff like wind farms and all this biofuel stuff. And considering all these positive feedback loops and everything, how it all kind of cycles together, wouldn't you also kind of see this lag time between where we start seeing the results of our actions in the data?
That lag time issue is very interesting. Gene actually showed a plot earlier, which he didn't mention that point, but if you looked at the rise in global temperatures through the 21st century, he talked about different scenarios, but all those rising curves were pretty much on track with each other until about the middle of this century, and then they start to diverge. So that's one way of expressing this one. Except for that lower curve, which is an unrealistic curve, because that would mean that all of a sudden we stop putting anything into the atmosphere after the year 2000. But all those other curves involve some attempt at a realistic scenario of increasing greenhouse gases. And you can see that they don't diverge until you get to the second half of the 21st century. So in some sense, steps we take now really aren't going to show up till farther down the road. And that, in some ways, that gets at part of the difficulty of trying to deal with things like cost-benefit analyses, because if you talk about mitigation, well, that's an immediate cost. We're immediately paying for higher prices for carbon, whether it's in terms of burning fossil fuels or whatever, but oftentimes a lot of the costs, a lot of the downstream costs in terms of impacts aren't going to really show up in a big way until you get farther into the future. And maybe there can be some innovation, as John talked about, to reduce some of those costs. But nonetheless, there's an intergenerational issue here. And part of this gets into how much are we willing to pay now to create what we hope is at least not a much worse world for the generations that follow us. So there are some lags like that in terms of how things we do now actually will show up in the future. In terms of your question about population, I remember this quote from Norman Borlaug, the father of the Green Revolution, who said that nothing that he had done would have any value in the long run unless we control human population. Now, that gets into some very dicey issues, very important cultural issues. But clearly, the more people you have trying to make use of the world's resources, the more people you have trying to live a lifestyle like we live in the United States, the more you're going to be burning fossil fuels, at least at this point, and the bigger demand you're placing on all sorts of human systems. So population certainly is a factor that gets involved with all of this.
John mentioned some cataclysmic climate effects that have to be avoided at all costs. One of those that comes to mind is the breakoff of the West Antarctic ice sheet, which would, if it happened, would cause sea level to rise essentially immediately by about 7 meters. So that's about 20 feet. And so that puts the southern third of Florida underwater. That puts Lincoln Memorial in Washington, D.C. underwater. It puts Washington Monument on an island. That's cataclysmic climate change. Is that plausible? We know that the ice is moving more rapidly on the Antarctic ice sheet. We know that it's being undermined by warmer water from below in areas where the ice is cantilevered out over the water off of land. And so it is accelerating. It's one of those high-risk, low-probability events, but we buy insurance for those kinds of things in our personal lives.
Since there's a quiet moment, I won't give up on another question here. And I really appreciate you doing this tonight, and I just read about it in the paper and came at the last minute. So anyway, how can you relate all of the things you've talked about to our current need, if you would venture into the politics of the bills that are being worked on now on climate change? I'd appreciate any comments you'd want to make about that.
John, you want to take that one?
I'll take a very broad shot. I'm afraid I'm like the Northwest pilots at 37,000 feet overshooting Minneapolis. But One of the things I think that I didn't say when I was talking about policy is that to be really effective, we've got to have global carbon policy. It doesn't do much good for the U.S. to have carbon policy. Obviously, if we got our emissions down, it would be a good thing, but we're part of a great big global issue. And that's why, I mean, if you go into issues like, if we put a tax on carbon and nobody else did, what would we do? We'd import all the things that we were made of or used a lot of carbon in their production and manufacture. So unless this is addressed on a broader scale, nothing's going to happen. I mean, in terms of improving the situation. In terms of the bills that are being discussed at the present time, most of the focus is going to cap and trade. I think one reason is that people in this country, probably all countries, really don't like taxes. That's a very negative thing. Everybody loves to campaign against taxes or for lower taxes. The thing about it is that the cap and trade doesn't set a price. But it does. Remember, if you set the cap at the right place, you're going to get the same price. And a cap and trade system generally is not going to be as smooth working as a tax would be. Because what you've got to do is you've got to build provisions into it that allow for some flexibility. With a tax, you can find ways of avoiding the tax by reducing your emissions, but you know what the tax is going to be all the time or what the price is going to be all the time. With a cap, you don't know what the price is going to be all the time, because if demand goes up, carbon is going to go up, or the demand for carbon permits is going to go up, and the price is going to rise. So it's going to create, in some senses, almost more uncertainty for industry than that ugly thing called a tax. The other ways of getting there, the low carbon fuel standard that California is using, I really don't think is a very good way of getting there. Because are we going to say that fuels have to be low carbon, or does everything have to be low carbon? Are we going to apply that criteria across the board? That's an administrative nightmare. It's kind of like dealing with indirect land use change, which has been a real issue in California and in the RFS 2, the Renewable Fuel Standard 2. And that's a real problem because nobody's quite sure how to measure it. Nobody can agree on how to measure it. And we're not even sure how big that effect is. You know, we've got one study that highlighted it, or a couple studies that have highlighted it. We don't know. And so I think in terms of where we're going with policy, I'm afraid we're going to try to manage the substitute fuels, the kind of research we do in the process, the technologies or platforms we use and so forth. We're not really going to try to address the carbon situation. What I feel, in one sense, is that we've always had a cheap energy policy in this country. You know, we're proud of the fact that we can buy our gas for, when I was a kid, for a quarter. And we can, buy it for $2 a gallon or less last summer one time. I don't think that's a great thing. I think it's awful. I think $4 gasoline would be a whole lot better. Why? Because then biofuels become competitive. $90, $100 a barrel of gasoline provides incentives for low-carbon alternatives without a bunch of incentives being provided by the government for particular fuels. One push that's coming down the road right now is for carbon equivalents. We subsidize based on the reduction in carbon as opposed to the particular fuel that's chosen. That makes much more sense. Because if wind energy is going to be more carbon saving than liquid biofuels, that may be the place we should be investing more money in the process because we're going to save more carbon. And to me, that's what's really critical. It's not picking which fuels are going to make it, which subsidies we put in. If you put all the subsidies in in cellulosic biofuels, they will go right now, pretty much, especially if the price of gasoline is $70, $80 a barrel. You don't need a lot more than that, but are there other alternatives that might be better? And are we going to subsidize those in a comparable way? And to some extent, what we're trying to do is get a fuel that can compete on price with gasoline, as opposed to trying to get gasoline to bring up the price of biofuels so they become a viable entity. So I think the process is backwards in a sense.
Okay, we have one last question.
There's been much talk lately about sequestering carbon with plants. And when plants, from my understanding of the decay process, that CO2, there's a certain amount of CO2 that is re-released back into the atmosphere when plants decay. And I was wondering if it would be a viable solution or if it is a viable idea that we have a carbon bank and, say, collect that biomass in the fall in, say, bales, if we were to, say, farm biomass and collect it in bales and have it in a permanent bank where it would not be able to decompose and re-release a certain amount of that carbon back into the atmosphere.
Yeah, it's plausible. It's possible. I think if you look at the cost of storage and the volume of storage that's required, it's pretty enormous. And because nature wants to if it's not protected from particularly from moisture, it's going to be it's going to decay back into the atmosphere again. So it's probably a study that could be done.
Actually, there is a study, well, Ray can mention biochar, but there's a study that was done or proposed, I think it was Environmental Science and Technology or something like that, last summer, to transport biomass and dump it into the ocean. Now, I was co-author of a rejoinder to that whole piece, or criticism of that whole piece. But one of the whole problems with biomass for fuels is the harvest, storage, and transport cost. And if you dump it in the ocean to sequester the carbon, you're going to incur those just as well. And so that's the real killer. And then, I think POET for their Emmetsburg plant estimates for 25 million gallons a year, it's going to take 100 acres, piled 25 feet deep, to supply that plant 300 days a year. I mean, that's just for a 25 million gallon plant. Think of what it would take if you wanted to capture a bunch of it and store it in the process.
Okay, so we'll we have one urgent question.
Hi,
Quick
I'm from the state of Wisconsin, and we had laws where we had to recycle tin cans and newspapers, etc. Where's the state of Iowa in putting legislation together to do more recycling?
We have a bottle law. In fact, I don't think they have a bottle return in the state of Wisconsin. So in that sense, we have a slightly different approach. Cans are voluntary, paper is voluntary. Here in the city of Ames, of course, we have a garbage burning power plant that recycles it all for us on a routine basis. So, I guess we'll call it to a close, and we thank you all for coming and for your interest in this topic. You can Google us and find us, I'm sure, if you have further questions and want to follow up on any of these issues. So thanks again for coming.